pair of gas-filled sacs possessed by many but not all species of fish. Comparing creatures both extant and extinct reveals this organ's evolutionary history, with connections to the emergence of lungs in air-breathing animals that Darwin himself remarked upon. Understanding the function of a swim bladder, however, requires a bit of physics. The low density of the enclosed gas offsets the high density of bone in bony fishes, allowing the animal to maintain the same average density as its watery surroundings, and thereby easily position itself at whatever depth it likes. A swim bladder is just one solution to the challenge of matching density. The fish might instead contain large amounts of low-density oil, or a skeleton composed of cartilage rather than bone, both of which are strategies adopted by sharks, which lack a swim bladder. The last common ancestor of cartilaginous and bony fish lived over 400 million years ago. Since then, the distinct evolutionary paths of the two groups have led to different solutions to the shared physical challenges of aquatic locomotion. We can state, with a point of view echoed throughout this book, that understanding the why of these anatomical features, related to control of density, highlights a hidden unity that fish share that transcends their evolutionary divergence. We should keep in mind, however, that the machinery of variation and natural selection, the enhanced odds of survival that accrued over generations to those creatures better able to navigate their aquatic world, provides the paths by which the forms we see arise. There are other vantage points besides those of biochemistry and evolution from which to survey the breadth of life. Rather than list all the approaches we won't be exploring, however, let's turn to the one we will. I've already hinted at the view of nature the rest of this book expands upon, which I identify as biophysical. The term implies a unification of biology and physics. It encapsulates the notion that the substances, shapes, and actions that constitute life are governed and constrained by the universal laws of physics, and that illuminating the connections between physical rules and biological manifestation reveals a framework upon which the dazzling variety of life is built. The notion of universality is central to the utility of physics and to its appeal. The same principles of gravity apply to an apple falling from a tree and to planets orbiting the sun, and current work aims to further expand this framework to encompass the strange behavior of the quantum world. Biophysics extends to the living world the quest for unity that lies at the heart of physics. To say that living things obey the laws of physics may seem trivial. After all, organisms are made up of the same fundamental particles that make up everything else, and are therefore governed by the same rules. But one might expect the explicit role of physics to be over after physical forces set up the formation of atoms and molecules, with complex chemistry giving shape to further molecular rearrangements, and the idiosyncratic predilections of cells and organisms being responsible for larger features. This is, however, incorrect. Just as physical forces direct the intricate branching of frost on a winter window and the rhythmic curves of vast desert dunes, and do so in ways that don't require subatomic particles for their explanation, physical mechanisms shape life at all scales. One of the great triumphs of physics, especially over the last half-century, has been an understanding of how broad rules arise in all sorts of natural phenomena, clearing the underbrush of complexity to reveal deep principles. Magnets, for example, become non-magnetic if heated above some specific critical temperature. Though magnets can be made of many different elements and alloys, each with their own unique atomic scale structure, the magnetic field of every magnet decays with exactly the same form as it approaches its critical temperature. Being a three-dimensional arrangement of interacting atoms, it turns out, suffices to determine the consequences of those interactions, regardless of atomic details. As another example, consider a shaken container of mixed nuts. One typically finds that the larger nuts rise to the top, giving this well-known phenomenon its name, the Brazil nut effect. The effect isn't particular to nuts, of course, and occurs in mixtures of cereal grains, rocks on riverbeds, and any collection of agitated, disordered objects. Its explanation involves general notions of what are called granular flows, and the ways